Hello and welcome to today's webinar. I'm Greg Johnston and I'm with Sensors and Software. And today's talk, we're going to be talking about ground penetrating radar today, or GPR. Sensors and Software is a Canadian GPR manufacturer founded in 1988. And I've been with Sensors and Software for 30 years. The topic today is SPIDAR SDK, which is a software development kit that allows users to control any of our GPR hardware. So this allows you, our customers, to integrate GPR technology into your own device. So my agenda today, I am going to do a few slides on GPR 101, just in case people need a little refresher on what this technology does. I'm going to talk about application-specific GPR systems from the early days, and then we'll get into the SPIDAR NIC hardware, which is what SPIDAR SDK is based on, and we'll talk about the specific GPR systems controlled by SPIDAR SDK, and then we'll get into some of the details of the GPR parameters that you can set up with the software development kit. We'll have a quick look at some sample code that's on GitHub, and we'll look at some example systems, some systems that people have been working on recently and over the last few years. And then at the end, we'll have a question and answer period. Okay, so that's the game plan over the next 45 minutes or so. All right, for those of you who are GPR experts, I apologize for the next 4 slides. But just in case we have some people who are not that familiar with the technology, here's a quick summary of what GPR does and what it's used for. GPR is a technology that creates an image of the subsurface by sending out a pulse of radio waves and collecting the reflections that come back from the subsurface. This creates an image of objects and boundaries in the subsurface that have different properties than the host material. In this example, GPR is imaging the buried concrete pipe. Conceptually, GPR is like a fish finder or an ultrasound, which you might be more familiar with. In all cases, waves are sent into the material and they reflect from objects in the subsurface to image and locate them. The difference is that a fish finder and an ultrasound use sound or acoustic waves. GPR, on the other hand, uses radio waves that travel much faster, closer to the speed of light. The term ground in ground penetrating radar is a loose term. Basically, any material that is non-metallic will allow radio waves to penetrate to a certain depth. This includes soil and rock, but also concrete, wood, plastic, fresh water, and more. The depth the signal penetrates the material being scanned varies depending on the properties of the material. GPR has a transmitting antenna on one end and a receiving antenna on the other end. The transmitter sends a pulse of radio frequency energy into the subsurface. Buried objects are identified by the signals they reflect back to the surface, which are detected by the GPR receiving antenna. The GPR records the echoes coming back for a period of time, equivalent to depth. The vertical strip of data under the GPR system is called a trace. Notice that the system is on wheels. It's designed to move and collect data in lines. As the wheel rotates a few centimeters, it triggers the transmitter to fire again, and another trace is collected. The vertical traces are combined to create a cross-section of the subsurface along the survey line. This is one of the most powerful features of GPR, the real-time view of the data. You can see objects on the data as you cross over them, but the data is also saved, so it can be replayed and reprocessed. This simple animation shows how an inverted V or a hyperbola is created when traversing over a point object. The apex of the V is the point of closest approach to the target. After you've crossed the object, you can pinpoint its exact location. This is GPR in a nutshell, and I'm sure that many of you already know this. The ability to image into the subsurface is useful for many applications. Here are the most common ones. If you've heard of GPR, it's probably when watching a show on the Discovery Channel about using GPR for archaeology to find ancient foundations, tombs, or artifacts. Or you've heard of GPR being used to scan a bad guy's backyard looking for a murder victim. It is also often featured on forensic shows like CSI, Bones, or cop shows such as Magnum PI. That's the exciting use of GPR. The more typical use of GPR is to find buried utilities for construction. Remember that one of the strengths of GPR is that it can find non-metallic objects, and many modern utilities are made of PVC, plastic, concrete, fiberglass, and other non-metallic materials. Another popular application for GPR is scanning concrete to avoid embedded structural elements like rebar, post-tension cables, and conduits that could be carrying power cables. GPR is also used in other fields, scanning roads and bridges, geotechnical applications such as identifying sinkholes before they become a major problem, agriculture and forestry, mining, military applications such as detecting mines and unexploded ordnance, and GPR is used in ice and snow. When you make hardware that can do cool things like Sensors and Software does with our GPR systems, you often hear things like, you guys should build a GPR system that does X, where X is go in a pipe, go on a drone, go on a robot, autonomously survey an area for landmines, crawl up a wall, go down a borehole, etc., etc., etc. In the 1980s and 90s, GPR systems were generic systems that could be used for a number of applications, but required an expert to run them effectively. This shut a lot of people out of the GPR market. In the late 90s, Sensors and Software started to release simple to use, what we called application-specific GPR systems. These are systems developed to perform one task very well that were simple to use so anybody could use GPR technology. Here are some examples. SnowScan was developed for measuring snow thickness on ski resorts. Conquest for concrete scanning was first released in 2001. Ice Map for measuring ice thickness on winter roads for safety. Those all came from the late 90s and early 2000s. People have interesting and creative ideas for hardware. For example, just look what happened with GPS once it was available to everyone. GPS is everywhere now, in your car, in your watch, your phone. It positions your photos. It tells a farmer where to plant a seed. It tracks your Amazon shipments. It even tracks your food delivery on Uber Eats. I doubt the people who invented GPS anticipated everything it would be used for. I think that it's just natural that when you make hardware that does something useful, people want to be creative with it. They want to integrate it in with their device and control it. To that end, we did this with GPR. In 2003, we released what we called the OEM Noggin. Customers were provided with a list of commands to control data collection over serial communication. It was slow, but it worked. This photo is from the University of Toronto Aerospace Engineering Department. They were working on a planetary rover that would use GPR to image the subsurface. In 2009, Sensors and Software released the first generation of NIC, the Network Interface Controller. This is hardware that controls our standard GPR products, such as noggins and pulse echo systems. In 2018, we released version 2 of the NIC. We call systems that use the NIC hardware to control one or more GPR systems, we call them SPIDAR systems. You may have heard about SPIDAR systems because they have been around for about 13 years now. SPIDAR GPR systems are very modular and flexible systems. You can build arrays of the same frequency or systems with multiple frequencies for different depths of penetration and resolution. Here are some SPIDAR systems that Sensors and Software and our customers have built and deployed over the years. Note that these systems all use the Sensors and Software data collection software. Earlier this year, we added the capability to the NIC for customers to control a GPR system through it. We call this SPIDAR SDK, SDK for Software Development Kit. Basically, we added a special module to a NIC so it will accept commands to set up and run a GPR system. This capability allows you to write your own GPR data acquisition software so GPR can be integrated into your system. NICs can control any of our noggin systems, which have antenna frequencies of 100, 250, 500, and 1,000 megahertz. Noggin systems are shown on the left here. NICs can also control pulse echo GPR systems with antenna frequencies from 12.5 megahertz, that's the very long ones on the top on the right, to 1,000 megahertz, very small ones there, the yellow ones. Pulse echo systems also have borehole antennas of 50, 100, and 200 megahertz. Any of these systems and frequencies can be controlled by a NIC in SPIDAR SDK mode. If we look at the connections, they are quite simple. There's a cable between the NIC and the GPR, but the cable can be virtually any length from 30 centimeters to 30 meters. The NIC needs 12 volts of power and an Ethernet connection to a computer. That is the minimum components of a SPIDAR SDK system. So you can see how simple it can be. This example shows a noggin system, and specifically a noggin 500 GPR system. This example shows the same setup, but for a pulse echo system with bistatic 250 megahertz high frequency antennas. So bistatic just means that there are two separate antennas, one transmitting and one receiving. You can see that, the two boxes here in the image. This is also a pulse echo system, but this time with 100 megahertz low frequency antennas. And as you saw in the other image, we have antennas down to 12.5 megahertz up to 200 megahertz. We consider those low frequency systems. Now let's look at the main commands that can be sent to the GPR system through the SDK. So not surprisingly, you have the ability to power up the GPR, basically turn it on. You can set up the GPR survey parameters, including how you're going to trigger the GPR system to collect data. And I'm going to talk a lot more about the GPR survey parameters to really get into the details here a bit. You can, of course, start data collection and stop data collection. Check for errors. There's commands there to check for errors. Were there any problems during the data collection? You can set the date and time. That allows you to do timestamps and things like that. And you can extract the date and time. So these are some of the commands, but basically you can see you can power up the system, set it up the way you want, collect data, and make sure there were no errors doing it. And then the idea is that you're going to take that data and you're going to do whatever you want with it. You can show it on the screen, or you don't have to show it on the screen. You can plot data or not, or you can save it till later and process it later on. So The world is your oyster. It's all up to you what you want to do with this capability. So I want to specifically dive into some of the details of the GPR survey settings. Those are the ones that, if you're familiar with GPR, you're going to be at least somewhat familiar with the settings, but I want to show you specifically the ones that we're able to use with the SPIDAR SDK. And the nice thing is there's not many parameters. And as you're going to see, they're fairly simple to set up and think about before you start data collection. So we're going to talk about antenna frequency, what frequency you're going to use, the time sampling interval, the number of points per trace, which is really related to depth. The more points you collect, the deeper you're going, the less points, the shallower you're going. The number of stacks, which is a way of increasing data quality. And then the trigger, how you're going to trigger the system, because your system could be doing anything. It could be crawling, it could be floating, it could be flying through the air. How are you going to be triggering it to collect data? So let's start off with the antenna frequency. With GPR, low frequency antennas generally provide deeper penetration, while higher frequency antennas don't see as deep, but they see with higher resolution. So that means that higher frequency antennas can see smaller objects and thinner layers in the subsurface. Therefore, the application is often tied to a particular antenna frequency or range of frequencies. For example, if you're studying glaciers or ice sheets or very deep geology, you're going to be using low frequency GPR antennas, 12.5 megahertz, 25 megahertz, 50 megahertz, in this sort of range. When you're getting into shallower geology, you're going to be in the 50, 100, 200 megahertz range. If you're looking at geotechnical applications, like for example, looking at sinkholes, you're probably going to be in that 100 megahertz, 200 megahertz range. Utility locating sits in the 250 to 500 megahertz range. Archaeology and forensics, often around 500 megahertz. And the very high resolution applications like scanning concrete for rebar, imaging a few inches in roads to look at the thickness of asphalt and that sort of thing. These are going to use the very high frequency, like 1,000 megahertz. So you can see that applications tend to be tied to different frequencies because they vary by depth and they vary by target size. So once you determine the frequency that's appropriate for the application that you have, next we have to set the time sampling interval. Sensors and software GPR systems are digital systems right at the antenna. This means that as the GPR reflections are returning from the subsurface, we need to sample the signals often enough so that by connecting the collected points, we can recreate the actual signal. So we record the red dots here, and we need to be able to connect all those together to recreate the actual trace. And so the distance between those points that we collect is called the time sampling interval. Basically, you want the time sampling interval to be fine enough to recreate the signal, but not so fine that it takes a long time to collect or gives you way more data than you actually need. With a coarse time sampling interval, this happens. You can see here, the recorded trace does not match the actual trace. And this is because the time sampling interval was too coarse for the data. So the recorded points cannot recreate the actual signal. This is called aliasing. Here's the same situation that you might be more familiar with. We know that the wheel is spinning counterclockwise, but because the video only has a certain number of frames or samples per second, once the wheel gets to a certain speed, the video cannot sample enough times to show the true rotation direction. And it looks like the wheel has stopped and is starting to rotate clockwise. This is called temporal aliasing. With GPR, if the time sampling interval is not sufficient for the antenna frequency, your data will be aliased and is not a true representation of the GPR signal. So high frequency antennas that transmit short wavelengths, shown on the right, can have shorter time sampling interval compared to low frequency antennas that transmit longer wavelengths, shown on the left. Therefore, the signal from low frequency antennas can be successfully recorded with longer time sampling intervals. So here are the recommended time sampling intervals for each antenna frequency in nanoseconds or billionths of a second. Again, finer sampling for higher frequencies and coarser sampling for lower frequencies. All right, let's look at the number of points per trace, which is related to depth. It is simple to understand that to record GPR reflections coming from deeper in the subsurface, you need to record signals for a longer period of time. This parameter is called the time window, more simple to understand, the depth. Since we are collecting digital data, we're collecting those points. If you're trying to see shallow, you don't need to collect as many samples or points than when you want to see deeper. That's not real rocket science. Less points will give you shallower data, and more points will give you deeper data. So if we look at this chart, if you're recording, say, 100 megahertz data at a time sampling interval of 0.8 nanoseconds, which is appropriate for that frequency without aliasing it, you will need to collect about 25 points for each meter of depth. So 1 meter, if you only want to scan 1 meter into the ground, you would need to collect 25 points. If you wanted to scan 2 meters in the ground, you're going to have to collect 50 points. 10 meters would require 250 points. And if you wanted to scan all the way down to 100 meters, if it was possible in what the environment you're working in, you would have to collect 2,500 points. It's obvious, but just in case, collecting more points takes longer than collecting less points. So that becomes a factor when you're actually collecting. All right, let's look at the number of stacks. It's important to realize that GPR systems don't just collect GPR signals generated by the GPR transmitter. GPR systems collect radio frequency signals in the bandwidth of the GPR receiving antenna. This means that some of the signals a GPR systems collects is external radio frequency from other radio sources, such as radio transmitting towers, cell phones, walkie-talkies, police radar. These external radio frequencies that we really don't want in our data are called noise. So if we look at this GPR cross-section, the bottom under the red dashed line shows noise, plotted as random signals, looking like a snowstorm or a TV station that's not coming in properly. Above the red line is the coherent GPR reflections from objects and boundaries. So as indicated by the red line, you can see the red line is at about 7 meters depth. And that is effectively the depth of penetration of the GPR. So if we look at the GPR signals, which on the right side is shown in blue, they have attenuated. As they get deeper, they've attenuated down to the same level as the noise level, shown in yellow. So that is the depth of penetration, when the GPR signal has attenuated to the same level as the background noise. That is as deep as we could see with the GPR. Because there's no way, there is GPR signal under the noise, smaller than the noise, but we can't see it because of the noise. So there's no way to differentiate the noise from the GPR signal. So since there's perfectly good but weak GPR signals buried below the noise, this means that the depth of GPR penetration will increase if we can decrease the noise level. That's shown in this animation. We decrease the noise and we see more of the GPR signal. Notice that the GPR line on the left is now a new section showing much greater depth of penetration than before. And now we see an object down here at depth that we didn't see before. So how do we decrease the noise level so we can see deeper with the GPR? The answer is stacking the GPR data. Let's talk about stacking. The idea of stacking is rather than collect the GPR data trace once and save it, we actually collect the GPR trace multiple times, average those multiple traces, and only save the average trace. For example, if we stack our data once, we fire the transmitter, we collect that trace, and we end up saving that trace. If we stack 2 times, we fire the transmitter once, collect the trace, fire the transmitter a second time, collect a second trace. We average those 2 traces together and we save the average trace. 4 times, we fire the transmitter 4 times, collect 4 traces, average those 4 traces, and save the average trace. 8 times, I think you get the picture here. But what I want you to notice is each time we stack more and more, the noise, which is shown here in red, is getting less and less and less. So what we accomplish is increasing what's called the signal to noise ratio. We're doing that not by increasing the GPR signal amplitude, but by decreasing the noise amplitude by averaging. The smaller we can make the noise, the more GPR signal we will see. The idea of decreasing the random noise is depicted here by the red part of the GPR trace. So notice how the amplitude of the red noise in the saved GPR trace gets smaller the more times we stack the trace. Here's an animation of GPR data collected over a metal sheet buried 3 meters in the ground. At low number of stacks, that's stacks of 1, 2, 4, 8, there's nothing but noise visible at 3 meters. So the metal sheet is not visible. But notice that as the number of stacks gets to 512, 1,024, 2,048 times, the noise has been suppressed enough to see the reflection from the metal sheet. This is how stacking can increase the depth of GPR penetration. Here's another example where targets are clearly visible when the data has been stacked 32,768 times on the right, compared to only stacking 256 times on the left. This is why stacking is a good thing, and why you always want to set your stacking as high as practical when collecting GPR data. All right, the last setting I want to talk about is the trigger mode. This is all about how do I tell the GPR system to collect data? Well, there's 2 ways. The first is using an odometer wheel to send a triggering pulse to the GPR system after that wheel has rolled the desired distance. Here are 4 examples of GPR configurations that use odometers to trigger the GPR system to collect data at equal intervals. Triggering method number 2 is called free run and is usually used when an odometer wheel cannot be used. Data is collected after a certain time delay, 1/10 of a second, 1 second, 5 seconds, whatever makes sense for the speed of the system and the target to be imaged. What we're trying to achieve is this: collecting as much data over our target so it's visible in the GPR data. The distance between traces is called the step size. We are trying to avoid this because 1 sample on the target is typically not enough to image it properly. And we are definitely trying to avoid this, where the step size is so large that we never collected any data over the target of interest. So here's a chart of the typical step sizes for the antenna frequency you are using. But it does also depend on the size of the target of interest. So these values may not be optimal and can be adjusted for your particular situation. Basically, with higher frequencies, we tend to be looking for smaller objects. So the step size tends to be a lot smaller. With lower frequencies, we're looking for larger objects. And so the step size can be much, much further apart. You see, we've got 2 orders of magnitude here in terms of from the very highest frequencies to the very lowest frequencies. So this may not have come across as simple, but what I'm trying to convey is that once you determine the best antenna frequency for your GPR application, you can use default settings for the time sampling interval. You can set the number of points to reach the depth you're interested in imaging. You can use a triggering method that's appropriate for your application. You can set a step size related to the size of the target and set stacks as high as practical to see as deep as you can. These are all the things that the SPIDAR SDK allows you to set in the GPR. So hopefully we've made data collection easy. SPIDAR SDK comes with sample code to get you going, get you started. SPIDAR SDK provides, we have documentation for all the commands to control a noggin or pulse echo system, and these are on GitHub. We also have sample code written in Python for basic parameter setup and data collection. So it gives you a place to start. The sample code is written in Python, but the data acquisition program that you write can use any programming language and any operating system for that matter. So if we jump on GitHub here, so if we look at, take a quick look at Sensors and Software SPIDAR SDK on GitHub, if we scroll down to the documentation, we can look at the GitHub pages. And under there, we've got devices controlled by SPIDAR SDK API. And if we go to the NIC, that will give us all the commands that we've been talking about. So for example, the system information, status, power, setup. If we go to setup, here's all the commands for setting up the GPR system, all the parameters, how they're defined, what the numbers mean, all that sort of stuff. This is all laid out in detail in our GitHub postings. Okay, so some of you are going to be a lot more familiar with GitHub than I am, but this is all the material that you need. And I mentioned that we have sample code to get you going. So you can go to the example folder here. And we got the .py, which is Python code. And this is a little routine, a program called collect data from NIC 500 SDK. And it goes through all the details of setting up all the parameters. starting, powering up the system, starting the system, collecting data end to end, and then shutting the system down. And so this is all laid out. I hope this is obvious, but just to be crystal clear, Sensors and Software does not provide training or support on how to program. If you are planning to use SPIDAR SDK, this is simply a skill that you must have or have access to. All right, let's finish off here. Let's look at some example systems. Here's some examples of systems that have been built over the last few years. Sensors and Software have done some of these. Our customers have created these. We've had systems for sewer inspection, mine safety, utility locating, airborne ice thickness, and excavation. So what I'm hoping is that this gives you some ideas for what you might be interested in developing. One of the first SPIDAR SDK customers earlier this year was Michigan Tech University, who's working on a project with NASA to integrate a noggin GPR into a lunar rover. And they sent us a couple photos here. You can see what the rover looks like, the size of the rover, and you can see a noggin 500 integrated in with the rover. So this is one of our first customers using SPIDAR SDK. So many problems are solved and informed decisions made with the ability to see what is below the surface before taking action. We hope that SPIDAR SDK allows skilled, creative people to use GPR in places that we never expected, much like the story of GPS. Maybe in the future, every Uber Eats driver will also inspect the road with GPR on their way to every delivery. So in summary, SPIDAR SDK is hardware and software that gives you the ability to integrate a GPR system into your device. Write your own data acquisition software so that you completely control the GPR. As you've seen, antenna frequencies are available for a range of applications. And certainly you can talk to us if you're not sure exactly which frequency would be appropriate for what you would like to do. And I just have to say this, that SPIDAR SDK is not for all our customers. It's for those that have the GPR knowledge, the programming skills, and the engineering skills to build something new, something that's never been created before. So on that note, I appreciate your time and your attention today. If you have any questions, please submit them on the chat. How can SDK, how can it benefit customers to build an MLDL? Machine learning and deep learning. Absolutely. So basically with a GPR, you're creating an image. And at that point, you can use machine learning to learn GPR responses, learn GPR patterns, and maybe identify objects. I think this is definitely, if you want to get into machine learning and deep learning with ground penetrating radar data, this is definitely a method of doing it. Do you want to test, study soil properties? Big question there is, do you necessarily need SPIDAR SDK? You probably need ground penetrating radar, but you may not need to write your own data acquisition software to study soil properties. You may just need a GPR system to collect the data and go from there. So you may want to differentiate whether, if you just need a GPR, we definitely have GPR systems that have their own data acquisitions software and also has data processing software. So you can look at the data and modify it and all that sort of stuff. SPIDAR SDK, on the other hand, we're talking about controlling all this stuff yourself. And as I say, you may not need to. If you just want to study soil properties, you may not need to. However, if you want to create a robotic device or something that is looking for certain things in the soil, and you want to do something that no one else is doing, then maybe SPIDAR SDK is what you want to do. Will the data processing part be available in the future? Well, one of the things that you can do is with SPIDAR SDK, you collect the GPR data and you can save it however you want. Now, one of your options is to save it as a sensors and software data file, save it in the sensors and software data file format, which are DT1 files and HD files. Some of you will be familiar with those. And so if you actually save it in that format, then you can use our Echo Project software to visualize and process the data the way you want. Okay, so that's an option. What triggering mode would be suitable for integration on drones? Well, definitely you're not going to have an odometer wheel rolling on the drone. So you are going to have to do it by time. You're going to have to do it in free run mode. And so it all depends on how fast the drone is flying and what the object is that you're looking for. So both those come into play. And so to answer your question, it would definitely be time, but you'd have to figure out the optimal distance between traces in time. So if you collected once a second and you flew the drone 10 centimeters per second, let's say, you'd be sampling every 10 centimeters on the ground. Is that appropriate? So you'd have to work out the details, and we could certainly help with that to get it right. But it would of course require some testing in the end to optimize those. RTK must be real-time kinematic. You're talking GPS, I believe. So the idea here is that we're not going to connect a GPS directly to the NIC unit. The idea is that you're probably going to have other hardware around the NIC, and that would allow you to input GPS information. So that's how we see that being done. And you would simply do one of the reasons why we have timestamps in there and the ability to extract time is because you're going to want to timestamp when you collected a GPR trace versus when you collected a GPS position, so that you can match those, you can integrate those, and therefore say that this GPR trace was collected at this position. Could I give more details on the visualization software? Well, again, that's wide open. The visualization software is either yours to write, or as I say, if you save the data, if you save the GPR data in sensors and software's format, you could use our Echo Project software to analyze and visualize the data. That is certainly an option. And I don't have images right now, but if you send me an email, I will send you a link. It's on our website. If you look up Echo Project on our website, you can see the type of visualizations that you can do with it. If you'd like me to send you that link, please send me an email and I'd be happy to forward the link so you can see the types of things. Basically, you can plot the data as cross sections. You can look at it as depth slices, and you can even get so far as plotting it in a three-dimensional data set if you desire. How many sensors using SDK? At this point, one NIC will support one GPR system. So if you want multiple GPR systems, you will need multiple NICs to go with them. And you'd have to get multiple SDK in order to do that. So you could, at this point, SPIDAR in general does allow multiple systems to run simultaneously, but in version 1 of SPIDAR SDK, we are only allowing you to control one GPR system per NIC. You would be able to have multiple NICs with multiple GPR systems. That's a possibility as well. No, daisy chain will not work with the SDK. So it's up to you to get them working independently and collecting the data. Thank you very much for your attendance. I hope you learned something, and definitely if you have questions, please contact me. send me a question and I'll make sure your question gets answered. Thank you very much for your attendance. So I'm gonna end the webinar now.